Hi everyone. So in this lecture of lecture 3 of week 9, we will look at explicit design methods for arbitrary pole placement. So and then we will also eventually prove that a necessary and sufficient condition for arbitrary pole placement is that the system should be completely controllable. Okay, so let's start with one of the very basic methods of pole placement. Okay, so what is the objective again? The objective is to find a feedback matrix K such that the closed loop poles have the desired locations from mu1 till mu n. Okay, so we will look at these three methods. Okay, so it should be controllable here. Okay. So, towards the end of the lecture we will prove this, that the K can be obtained if and only if the system is completely controllable. So, we will first start with the direct substitution method. Okay. So, let us say I am looking at a third order system. So, my feedback law u equal to minus kx will be of the form say minus k1, k2, k3, x1, x2, x3, and will be given as minus k1 times x1, k2 times x2, minus k3 times x3. Okay. So, what is known to us? I know A, I know B. Additionally, what do I know is that additionally I also know the closed loop characteristic equation. Okay. Where does the closed loop characteristic equation come from? That comes from the location of the decide pole. So, I have S minus mu 1, S minus mu 2, S minus mu 3. Okay. So, everything in this expression is known to me. Okay. Now, what is unknown? Unknown is these three numbers k1, k2, k3. Okay, now what is the characteristic equation of the closed loop system? That will just be the determinant of this Si minus A plus Bk. Okay, where does this come from? If I just look at x dot equal to Ax, I am looking at the characteristic equation of this form Si minus A equal to 0. Now, if I have input to the system, x dot is Ax plus Bu with u of the form minus Kx, then my system, closed loop system, takes this form. A minus Bkx, and the poles will now correspond to the characteristic equation which is obtained by this matrix A minus Bk, and therefore, the closed loop characteristic equation will be of this form Si minus A plus Bk, and all the unknowns now are in this matrix K. Okay. So, now this kind of looks, so on the left hand side I have an equation of all the, or everything is known to me. On the right hand side I have equations of three unknowns, and I can just solve it via some simple simultaneous equations. Okay, I will just do a very small example on this. So, I have x dot is A x plus Bu. Okay, go back to the black color. Okay, where A is 0, 1, 0, 0, 0, 1, minus 1, minus 5, minus 6. B is also of the form 0, 0, 1, and it is easy to check that this is actually in the controllable canonical form. Right. Okay. So, let us say I want to place my closed loop poles in the following locations. So, these are the decide poles. So, one pole is decided to be at 2 plus J4, the other would obviously then be at 2 minus J4, and the third pole would be at say minus 10. Okay. So, first is, okay, check if the system is controllable. Well, the answer is yes, right? The system is actually controllable. I will leave the steps for you to verify that, you can get easily check that the rank of C is equal to 3, and also because I have it in the controllable canonical form, the system is actually controllable. Okay. And the characteristic equation of the uncontrolled or the open loop system would just be of this form: S cube plus 6 S square plus 5S plus 1. Okay. This is what is given to me. So, now based on the closed loop poles, can I find out what is the desired characteristic equation? Okay, that will be from S plus 2 minus J4, S plus 2 plus J4, and S plus 10, right, from here. So, this is how the closed loop characteristic equation knows, and I know what is mu1, mu2, mu3, which are essentially these 3 numbers here. And this looks in the following: this is S cube plus 14 S square plus 60x plus 200. Okay. So, now what do I need to find? So, I know this, right. Now, I need to find what is u equal to minus kx that achieves this. So, u will be of the form minus k1 x1 minus k2 x2 minus k3 x3, or I am looking at the characteristic equation of the closed loop system, which is Si minus A plus Bk. Okay. Now, if I compute this, in terms of these unknowns k1, k2 and k3, it turns out that the closed loop characteristic equation in terms of the unknowns k1, k2, k3 is, I am just looking at the determinant of this. So, this will be S0 0 0 S 0 0 0 S minus 0 1 0 0 0 1 minus 1 minus 5 minus 6 plus 0 0 1 k1, k2 and k3. Okay, I can expand this and then find it to be of the, this is S cube plus 6 plus k3 S square plus 5 plus k2 times S plus 1 plus k1. Now, I can actually compare the coefficients now, right. The coefficient of S square here is 6 plus k3, which must be equal to 14, okay. And therefore, k3, so with these two I will have 6 plus k3 is 14, which means k3 is 8. Similarly, I can look at the coefficient of S, right. So, 5 times k2 times S is 60, and therefore, k2 is okay, sorry, there should be so this should be 5 plus k2 times S. Uh, 5 plus k2 is 60, therefore, k2 is 55, and the last expression says 1 plus k1 is 200, and therefore, k1 is 199. Okay, that looks pretty neat and straightforward, right. I can do everything with hand, but the drawback is if as n becomes much larger, these computations become tedious to do by hand. Okay, now what is the second method? The second method comes via the controllable canonical form, right. So, assume that my system is in the controllable canonical form. If it is not in the controllable canonical form, I actually know how it works, right. I will tell you how to even deal with a system which is not in controllable canonical form. At the moment I assume that let the system be in controllable canonical form. Okay, again I will do it for the case of the CISO system, and again my problem is to find these unknowns k, which is from kn minus 1 till kn. Right. Again I am now looking at the closed loop characteristic equation, again obtained by Si minus A minus B times k. Okay. Okay. Let us actually do this do these computations and check where we are. Okay, where do I start from? So, I start from assume the system is in the controllable canonical form, that okay, and also assume that n equal to 3. So, that my computations become easy and they also look a little neat and would not look too tedious. So, I have minus A3 minus A2 minus A1. This will be my A matrix, B will be of the form 0 0 1. Okay. Now, what do I know? I know the following, right. I know the closed loop poles, so the same steps like here, right. So, I know the desired poles. So, with the desired poles, let them be at some arbitrary mu1, mu2 and mu3 such that S minus mu1, S minus mu2, S minus mu3 expands to this one Sn plus say alpha 1. So, okay, for the case of n equal to 3, this will be S cube, alpha 1 S square, alpha 2 S plus alpha 3, right. So, all these are known. So, the mu's and alphas are known, or they are given to us, right. Okay. Now, what should I find is what is k? Right. So, I compute closed loop characteristic equation, which for the case in the 3 by 3 case will just be like this, right. So, I have Si minus A, which is 0 1 0 0 0 1 minus A3 minus A2 minus A1, okay, plus I have a B times k here. So, I have 0 till 1 times k3, k2 and k1. Okay. So, how will this look like? So, this will be a S here, a 1 with a minus, a 0, a 0, a S, another minus 1, and here will be A3 plus K3. Here we will have A2 plus K2, and here we will have A1 plus K1. Okay, and then I am looking at the determinant of this, and this turns out that it will be something like this. I have Sn plus A1 plus K1. So, in this case I am looking at S3, S3 S square, then I will have A2 plus K2 times S, and then eventually A3 plus K3 times S equal to 0. So, I just look at these two equations now, right. So, this which okay, this is a characteristic equation, this, and then I go about comparing the coefficients. Now, okay, what do I have? I have now from the first term is that A1 plus K1 is alpha 1. Okay, I know what is A1, that comes from my given system. I know what is alpha 1, that comes from the desired roots. So, therefore, I can compute K1 as alpha 1 minus a 1. Similarly, I will have a 2 plus k 2 by equating the coefficient of s here with the coefficient of s, that is alpha 2. E 3 plus k 3 is alpha 3, and so on if I have a system of dimension n. Okay. Now, so this is okay. What's a subtle difference between here, right? So here, if I know, okay, what is do I know a1? Well, a1 is directly given from here. Do I know alpha 1? Well, the answer is yes. Okay. So give me this and give me this, I can directly compute what is the k1. Similarly for k2 and so on. A little distinction from here is that we were trying to explicitly compute the closed loop characteristic equation in terms of k1, k2, k3 and so on. But here, okay, just give me these two numbers, and so this can be obtained. The alphas can be obtained by the closed loop characteristic equation. A1, A2, A3 are known to me. Okay. So a little caveat, and which is not very bad for us, is that the system is assumed to be in the controllable canonical form. So the k I obtained here is in the controllable canonical form. Okay. And let me assume now that, well, system is not in the controllable canonical form, but I get it into the controllable canonical form via some transformation x equal to t x cap. Okay. And the system in x cap is in the controllable canonical form. Okay. So the k I compute here, the k I compute in the controllable canonical form would just be related to the original k via just this transform. Okay, that's an easy process to check. So if I do not have the system in the controllable canonical form, so we will just write the steps, right. So if I do not have the system in the controllable canonical form, first transform it into this controllable canonical form via x equal to t x cap. Okay. Now compute k, let me call this k cap because I am looking now at the controllable canonical form using these formulas here, right, that okay, what did I have, a1 plus say small k1 cap is alpha 1 and so on. Okay. Now what is the original k? Original k for the system in x, well, all this was in x cap, right. Well, the k turns out simply to be k cap times t inverse. Okay. It's a very straightforward thing once you understand how one can arrive at the similarity transformation, right, starting from any given system. Okay. So that's pretty easy and neat. So I'll just do the last thing, which is a little tedious, but it's nice to know the Ackermann's formula. Okay, this might look a little ugly and tedious, but let's still do it. So I have x dot is a x plus b u, which I transform via u equal to minus k x to x dot is a minus b k x, which I also call as a tilde x. Okay. Now, what is the characteristic equation of the closed loop system? Characteristic equation of the closed loop system is S I minus A plus B k is S I minus A tilde, that will be again S minus mu 1 S minus mu n. So, all these closed loop poles are given to me, and I can expand this and write it in terms of the coefficients of the polynomial in S. Okay. Now, okay, so this is good. Now, let me go to the Cayley-Hamilton theorem. And what it tells me is phi of A tilde is that a matrix satisfies its own characteristic equation, alpha 1 A n minus 1 plus alpha n minus 1 tilde plus alpha n I equal to 0. Now, this is the n cross n identity. Okay, so what do I know that A tilde is A minus bk, A tilde square is, well, I just expand this, A minus bk square, and I can write this as A square minus A bk minus bka minus bk times bk. I can also write this in a little simplified way as A square minus A bk minus bk A tilde. Similarly, A cube can be written as A cube minus A square bk minus A bka tilde minus bka tilde square. Okay, I will just do the proof for n equal to 3 again for simplicity, and then to avoid ugly looking computations. Okay, now I put all these values into the characteristic equation, and what I get is the following. So, I am looking at alpha 3 with the identity plus alpha 2 A tilde, alpha 1 A tilde square plus A tilde cube. Okay, so I will skip some steps and just write down how it looks in final. So, I will have some terms to do with alpha 3 I, alpha 2 A, alpha 1 A square plus A cube, all this in A. Then I will have minus alpha 2 bk minus alpha 1 A bk minus alpha 1 bk A tilde minus A square bk. Okay, so we have again that phi of A tilde is 0, right, and okay, what can I then say in terms of phi of A? Phi of A, which looks like alpha 3 I plus alpha 2 A plus alpha 1 A square plus A cube is phi of A, and this is not 0, right, because A, these alphas are the coefficients for the characteristic equation corresponding to A tilde, and therefore, they will not be the coefficients corresponding to the matrix A, and therefore, phi of A will not be 0. But I can write phi of A tilde now as, okay, see the entire thing here is phi of A. Okay. So, this is phi of A minus alpha 2 bk minus alpha 1 A bk minus alpha 1 bk A tilde minus A square bk. Okay, this will have two more terms here, minus A bk A tilde minus bk A tilde square. Okay, so I will just put them up here too, A bk A tilde minus b k a tilde square. Okay, now this phi of a equal to 0, sorry, phi of a tilde is equal to 0. Okay, now, so I can, so this entire thing will equate to a 0 here. Okay, so phi of a minus all these terms will equate to 0, and this will simplify to some nice looking term here, that okay, I just take phi of a to the left, and what I will be left is b a b a n minus 1 b, and I will have some terms here at alpha 2 k and then k. Okay, so okay, something looks nice here, right? So I just want, if I just can do some magic to just find what is this k, then I am done. Okay, I'll just skip. I just keep skipping all the steps here. Okay, so for controllability, this matrix should be invertible if I am looking essentially in the single input single output case. So let me call this just C, and I can now write this equivalently as C inverse of phi of A is this entire matrix here with some term star 1, some term star 2 and a k. Okay, but I call this as star 1, I call this as star 2. Okay, nice. So I just again want to do something here, right? So if I just multiply to the left of both sides by 0 0 1, this will be 0 0 1 times star of 1 star of 2 k. Okay, what is this? This is just equal to k, and I just now look at this and this. It turns out that the k is simply 0 0 1 C inverse, okay, phi of A. Okay, this is the what is called as the famous Ackermann's formula. Okay, so that's what is we derive through the Ackermann's formula. Okay, so I'll just have this example. I just leave for you to solve this. It's again same application of the methods that we had over here, right? Okay, and I'll maybe put up the solutions when I upload the slides. Okay, right. Before I started this lecture, we said that we should, or there were some hints that controllability should be some kind of a necessary condition for pole placement, right? So you can start from the controllable canonical form. Something similar was also seen in the Ackermann's formula, where you needed invertibility of the controller matrix. So let's spend some time and prove the following, right? That the necessary and sufficient condition for arbitrary pole placement is that the system is fully controllable and observable. Okay, so then both system is, so what does it mean? So if I can place the pole placement is equivalent to system being completely controllable. Okay, so let's start with part 1 of the proof, right? Let's say system is not completely controllable, okay, which means that the rank of C, which is B, sorry, till a n minus 1 b, let it be some q which is less than n. Okay, in that situation, what I know is I can transform system into its controllable part and its uncontrollable part, right? Okay, so So, I assume that there exists a transformation that will take my system from its starting from its original form to the controllable decomposed form, right. Okay. Now, this is easy to check, that if I have the characteristic equation in A and B, this will be the same as having the characteristic equation in A cap, where A cap, B cap and all, they correspond to the controllable canonical form. Okay. Now, how does this expand to? So, I just look at this term here, this will be S I minus, okay, what is A? A looks something like this, AC, A12, 0, AU plus B will be BC, 0, some KC and some KU. Okay. So, this will be now of the form. So, I am looking at the determinant of this. So, this will be S I Q. So, this A is a Q cross Q matrix here, right. So, this will be S I Q minus A C plus B C K C, all these controllable terms. Here I will have a minus A 1 2 plus B C K U, 0 here. Here I will have S n corresponding to this A U would be of dimension n minus q. So, the identity of n minus q minus A 2 2, the determinant of this should be 0, which essentially means that I have S I Q minus A C plus B C K C times S I n minus q minus A 2 2 is equal to 0. Okay. So, I start with a system which is of the form x dot equal to A x plus B u, apply a control law of the form u equal to minus k x, and I assume that the system is not completely controllable, which means I can decompose it into this controllable and uncontrollable forms, and I look what happens with the application of control to the closed loop characteristic equation, right. So, what I know is that the closed loop characteristic equation will tell me where the closed loop poles are. Okay. So, look at this, right. So, what is the difference between the closed loop poles of A22 and its open loop poles, right. So, they are the same, right. Open loop, sorry, I should call this AU, right, this to be consistent with the notation here, right. So, this should also be AU. Okay. So, this control law does not alter the poles of AU, there is no change in poles here. Due to u equal to minus k x. Okay. Or in other words, the closed loop eigenvalues of A22 do not depend on k, and therefore, if the system is not completely controllable, I cannot place the poles of this part, of the uncontrollable part. Okay. So, this completes one part of the proof. The second part of the proof would say that, okay, start with a system which is completely controllable, start with the system and then prove that one can place all the poles of the closed loop system at the desired locations. Okay, so I just go back, I know do the proof, not repeat it over here again, but what we saw, say for example here in this example is that, okay, so if I have a system which is in this form, this system is of course completely controllable. Okay, it is in the controllable canonical form. If it is not in the controllable canonical form, I always know how to get it into the controllable canonical form. So, what was the conclusion here is that if the system is in this form, then I can always place the closed loop poles according to this formula. I can always compute k1 till kn, right. So, what does this mean, right? I start from a completely controllable system and I show that I can place all the poles, or a solution to this exists, right, starting from this given characteristic equation to this unknown equation always exists, right. So, that is also a proof of saying that, well, start from a completely controllable system, then you can place all the poles of the closed loop system at the desired locations. I will not write on the steps, but I think that is kind of very obvious from what we saw over there. Okay, so that's kind of writing down the text over here again. So, what we just saw is three methods of placing the closed loop poles. One from directly comparing the open loop and closed loop characteristic equation. Second is write down in the controllable canonical form, so that the formulas become much easier. And the third was a little more involved one of the Ackermann's formula. Okay, so what we will do is also have a little tutorial session where we solve a bunch of problems, including partial pole placement, how to even handle these pole placement problems via MATLAB, and a bunch of other practice problems that we will post online. And I hope that helps a bit in the learning process. So, this concludes a lecture on design, controller design, assuming the system was fully like all the states of the system were available for measurement, so that I could just do u equal to minus kx. The question is, what if all the states of the system are not observable, are not observable. That would lead to then say, okay, then I need to do something else. Can I do an observer design? Can I add on top of I just have the output measurements, can I make use of the outputs to construct the states and then feed back those states to get the appropriate control design, right. So, that will come up in next week's lectures in terms of observer design, and we will also look at simultaneously how to design controller and observer, and also see if designing an observer, does it really affect the control part, or and vice versa, right. So, we will see this both together. That will come up next week. Thanks for listening.